David Smith here with another Flip Classroom video. 3 tips before we start. First, remember you can pause the video anytime to catch up with your notes. Second, you can turn on the captions below so you can watch my words go by on the screen. And lastly, you can play the video at double speed if that helps you get through it faster. Today's lesson is going to cover how to use integration to calculate the area between 2 curves. Now, if you're in my class, you realize that the last couple lessons we did was calculating the area under a curve, which is basically the area between a curve and the x-axis. Now we're going to throw a second curve in there, and we're going to calculate the area between the 2. Now you already have all the tools to do this with all of our properties of integrals. We're just going to do it in a new concept, in a new context. So let's take a look at our definitional start, then we'll throw up a graph, then we'll do some problems. So check this out. So if y1 and y2 are continuous functions, so this could be f of x and g of x, something like that. Okay, so y1, we're just using y1 and y2 in our definition here. So these are our 2 continuous functions, and y1 is bigger than y2 on this interval. So between a and b, as long as the x value is between a and b, and y1 is bigger than y2, then the area between the curves is given by the integral from a to b of y1 minus y2 dx. And I realize I missed something. There we go. That's area. So this is how to do that. And you'll remember from our properties of integrals, we definitely have a property that lets us deal with that. So let's throw up a graph and show you what we're talking about graphically. All right, so here you go. Here's my graph. I have this function here, this curving function like so. That's our y1. We're not talking about what the actual function is yet. We're just doing this in the graphical picture to kind of illustrate this definition here. So here's my y1 curving this way. Here's my y2. It looks like pretty much a straight linear function, and it's just an increasing function that way. And so the area that we're after is the shaded region between the 2 curves, and that's on the interval from A to B. Now you'll notice that it fits the condition because between A and B, y1 is bigger than y2. So on A to B, y1 bigger than y2. Later, we'll talk about how to calculate the area between a curve when you have an interval that includes sections where y1 is less than y2 and how we do that. But right now, we're just going to focus on the section where one function is bigger than the other, so we can calculate that area. So here's the area, and the area is the integral from a to b of y1 minus y2 dx. So this is the whole thing about what we're going to do in this lesson. So let's do an example. Okay, here is a paper 1 question. So no graphing calculator on that. So you're going to find that the functions are more straightforward, so you can use a graph to do the things you're going to need to do. So we're going to do that right now. So find the area of the region bounded by y equals 4 minus x squared. There's a quadratic right there. And y equals x plus 2. There's a linear function there with a y-intercept of 2. Okay, so your first step here is let's make a graph of what we've got going on so that we can get a better picture of that. You might have a prompt to make a graph, or if you don't, you still might want to do it just so you can see what's happening. All right, here's my graph. So this is just a downward facing parabola with a y-intercept of 4. We could rewrite this equation as negative x squared plus 4. So we know that it's a regularly shaped parabola. It's not wider or narrower. It goes down because we have a negative there, and this tells us that the vertex is at the point 0, 4. So I just drew it going right through there. Okay, so that's our curving parabola. And then y equals x plus 2, that's a linear equation with a slope of 1 and a y-intercept of 2. So that is the point 0, 2 right there, and it's going up by 1. So I've drawn my graph. Now I need to do some critical thinking about my interval. Like, how am I going to calculate this? Okay, let me rephrase that. The area of the region bounded by. Okay, so there's only one area, and that would be this one right there. That's the region bounded by the 2 curves. Okay. okay? So we're not given the interval, but we do need to know the interval to be able to do our integral. So check this out. The only part that's bounded is right in here, because here we don't have that anymore. This is bounded, completely surrounded by the two functions. So that is one of our spots, and that's the other spot. So right now you could probably get a feel for what that is. You know, let's do this algebraically. Remember, paper one problem, so we have to do it algebraically, which means, critical thinking step, we have to find the 2 points of intersection, because the x values of those are going to be our a and our b. So for example, we could just make a little line down there. That's our a, and that's our b for our integration. So we need to find those points of intersection. So if you recall, the way you do that is you set this equation equal to that equation, and you solve. Paper one, we've got to do this by hand with algebra. So go ahead, set 4 minus x squared equal to x plus 2, and solve that equation. So a little quick quadratic solving with some factoring. This is a super easy one to do. I set my two equations equal to each other. I moved everything over to the other side because I really like my quadratic term to be positive. It's just more helpful. So I have 0 equals x squared plus x minus 2. I can factor that out quite easily to x plus 2 times x minus 1, which gives us the two solutions of x equals negative 2 and x equals 1. So what that tells us is this is negative 2 and this is 1. So now we know our a and our b for our integration. Okay, I'm going to do that right over here. So now I've phrased my integral from negative 2 to 1 of the function that's above the linear function. So that's my, my quadratic function. That's my linear function. This is the bigger one of the two over our interval. This is the bigger one of the two over the interval. So that's the one that comes first. And then we subtract the other function from that dx. So now you have enough tools to go ahead and figure out the value of that integral. Go ahead and pause the video and see how far you can get with that. Okay, so now I want to show you the next couple steps, but I'm still going to hope that you can pause that video then and finish this out. So what I did is, first off, we can just combine all these terms. It's pretty simple. I don't have to expand anything. I don't have a binomial squared. I do have a squared term, but my parentheses and stuff just let me combine my term. So I went ahead and did that. Minus x squared minus x plus 2. So there's the function that I'm going to integrate over the interval minus 2 to 1, right there, to 1. So this one, I can just use the integral power rule on each term, and I get minus x to the third over 3 minus x squared over 2 plus 2x, and then again, over this interval, minus 2 to 1. So this is our capital F function. That's the antiderivative, which is the integral. So I'm just bringing some of that notation along just to kind of help clear our thought process. So now, if you remember from before, what we're going to do is we're going to subtract the top one from the bottom one. So we need to do antiderivative or integral with 1 plugged in for x, and then subtract the antiderivative integral with 2 plugged in for x. So go ahead, pause, do the plug-in step on that one, and see what you get. Boy, sort of a lot of computation in that one. So let's take a look. So here is my prompt for the plug-in step. I left you with that one on the last time. So here is my plug-in step. Lots of plugging in. There's 6 things, right? Our antiderivative, our integral, has 3 terms, and we've got to do that twice. So I plugged in my 1 here for x in my antiderivative. And I just did a straight up plug-in step, didn't do any other thinking, and then I plugged in my minus 2 in here for the integral antiderivative. The rest of this is just simplifying it on down with all these fractions and stuff like that. So go ahead, pause the video if you need to check your work with this to this to this to this, finally getting down to 4.5 or 9/2. Now let's do one that relates where we can use technology, where we can use the graphing calculator to do the integral.
Okay, so I'm going to pop over onto Desmos and do one of these problems using the graphing tool so that I can pull out my intersections and also just to visualize what I'm doing. So let's pop over there. Okay, here we are in Desmos, and if you look at the upper left, you're going to see here are my 2 functions. I have e to the 2x plus 1, and I have x plus 4. So I have a function with the natural log in there with an e, and then I have the straight up linear function. So I'm going to go ahead and turn those on by clicking them here. And there's my graph in the center. Now let's zoom in a little bit just so we get a better picture of what we're looking at. And there you go. So here's my graph. Now, this gives me the visual representation of how these two curves interact. And the main purpose here of pulling up the graph is so that I can find the intervals, that's one, and figure out which is the bigger function over the interval. And so I can see quite clearly here that it's the blue line, which is the x plus 4 function. So that's going to be the one that's the larger one, and I'm going to need to subtract the other one from it. Now I need to know what those points of intersection are. And so in Desmos, that's pretty easy. If you just click on one of the functions on the graph, I can get this point, I can hover over there. So the point of intersection for the leftmost one is going to be minus 3.00, comma 1.00. So remember, 3 sig figs, we don't need to carry a big pile of decimals into our calculation. We can just use that. Now let's hover over the other point of intersection. That's 0.647. We're going to use that. 0.647. That's rounding to 3 sig figs. Let me move my little away here to get the other one. What do we got? We got 4.65. 4.5. Now really all we need are the x coordinates because that's going to determine how we do our integration. So let's go ahead and pop back to the board and take a look at how that goes.
All right, so that Desmos graphing little side journey we took, here's how that would look with an IB problem prompt. First off, I'm going to tell you this would be in a paper 2. Okay, so you would go, yes, calculator, I can use that. Find the area. I don't know what it is about the A in area that I keep forgetting. So find area bounded by f of x equals e to the 2x plus 1 and g of x equals x plus 4. Now, we don't know what the interval would be, and we don't know which function is bigger or smaller. So the graph is super important. Now, doing a hand graph for this might be a little bit harder than that last one, especially for the e to the 2x plus 1. So if you're not super familiar with that, plus you might just go, hey, I got a calculator, let's throw that bad boy in there. So we did that, we got our numbers, I went ahead and summarized them with a hand graph over here, so we can just have that for our references as we work the problem. And indeed, here's our area shaded like that. Okay, so your first challenge, express this problem in terms of an integral. So go ahead, pause the video, use all the information we have, and write the integral. Okay, here's our integral. I put the x plus 4 function first because we know that's the bigger one on our graph over our interval. I put my intervals here next to my integral sign. So here's the prompting for the integral. Here's the actual integral. We're going to have to integrate this. Now, the next step is let's simplify that because, again, we don't have any binomial powers, so we don't have to worry about some big old expansion using chain rule, things like that. We can just combine terms and simplify this on down. So pause the video and do just that. Okay, so here's the simplification of our integral. Now, actually, maybe I should apologize. I led you a little bit astray. We're on a paper 2 question. So we didn't need to do this step. All we needed to do was put this integral into the calculator. And as long as we enter it in correctly, we will get the right result. We don't need to simplify it any further. The calculator will take your interval and take your expression and integrate it and do the calculation and spit out the answer. So why don't you go ahead and do that? I think this one's a little easier to enter. So pause the video, pull out your calculator, whatever technology you use to do calculator-y stuff, and go ahead and run that integral through there and see what you get. Here is what I get, 4.83. Pretty cool, right? I mean, if we did this algebraically, if we did this on paper, boy, it would take a lot. But the calculator just took us right there. One last problem. Yes, getting a little more tricky. Let's look at the prompt. Actually, nice thing, this is a paper 2. okay? I'm not saying that you couldn't have this be a paper 1, but it would be a toughie. It would take a lot of work. So let's just start there. Paper 2. So you're going, yay, calculator. Okay, so check this out. Find the area of the region between the curves of this and this. So it's a little bit more generally stated. And you know here we have a cubic function, and they tend to kind of wiggle around a little bit. So you definitely want to get on your graph and see what you get from that, because it's going to be a little bit more complicated than the last 2 problems that we did. So go ahead, pull out your graphing calculator, pop over to Desmos, whatever you do, and put these 2 functions in there and take a look at what you get. Okay, I went ahead and went into my graphing software. I graphed these 2 functions, and I've tried to reproduce that as well as I can on the board. My graph is maybe not perfect, might not match quite what you've got, but I caught the essential elements of it. In fact, that's all you've got to do with your graphs. So first off, here is the origin, and all 3 of these things are, well, the origin, both functions intersect right at the origin there. So here is my f of x equals x squared, I'm sorry, my g of x equals x squared, standard parabola, mother function for every quadratic function. Okay, so it's the simplest parabola we got. And then here's my cubic function, which comes up, has a local max, comes down, has a local minimum, and then goes on up. So the interesting thing here is I've shaded my regions, and I have one region where f of x is the bigger function, and then I have a second region where g of x is the bigger function. So I'm going to need to do some things here to make sure I take the right integrals. So to get the area of the region between the curves, which I have now found out, there's 2 regions and they need to be calculated slightly differently. I need to have this point, and that point. So I kind of need like my A, we could call that a B, and we could call that a C, if we like. And then what I would do is I'd do an integration from A to B of this function of the g of x minus f of x, and then I do an integration from B to C of the g of x minus f of x. I think I said that backwards. From A to B is f of x minus g of x, because f of x is the bigger function. Okay, so let's see, next prompt. Just write a very general statement of how you're doing this integration to without putting any functions in there, just using f and g and the integral sign and the intervals. Okay, I looked on my calculator to get a little bit more information because we are going to need those intervals. And it turns out this function is written in such a way that these are nice numbers. So obviously we know this one is at the origin, so the a is 0. B turns out to be 1. That's one solution to these 2 functions. And then our C ends up being 3. So that's kind of nice. This problem is staged to be nice. Just remember that yours may not. You may have some decimals, and you might need to use 3 sig figs like we did in the last one. So check this out. What we're going to do is we're going to add this area to that area. This area is f of x, the bigger one, minus g of x, and this area is g of x, which is bigger, minus f of x. So all I've done is I've written that out here with integral notation. So this is 0 to 1, f of x minus gx of x dx, and then we're going to add from 1 to 3 of g of x minus f of x dx. So that's stated all out. Also, just in general terms, though, unfortunately, we can't use this and the calculator, which is definitely where we're going to go with this problem. So I want one more step from you, and then if you're feeling bold, go ahead and put that in your calculator, and let's get the answer to this integral. Okay, so even though we get to avoid doing all the algebra because we're really happy about that, because doing all of these, that's lots of plug and chug, lots of opportunities to make little mistakes that affect the overall answer. So we're happy we don't have to do that. Go ahead, if you haven't already done so, and put that in your calculator and make sure you can get a result. And when you have one, come back and compare. Woohoo! Pretty amazing, right? 3.08. Whoa, I mean, in this class, a lot of our stuff doesn't boil down to one number. And I don't think we have situations like this that are as complicated as this, that boil down to just one number. I think it's pretty cool. We start off with this big old graph. We had to interpret the graph in terms of the question. We noticed we had two areas that we needed to calculate. We needed to figure out which function gets subtracted from which function for each area. We had to express that thought in terms of an integral. We had to do a plug-in step with our general integral, with our general functions in our integrals to get our actual functions integrated over the ranges that we needed to integrate them over. And we had to pull out a calculator and put all this stuff in there. Phew, lots of steps, lots of terms. We've got 8 terms in here. We've got 2 ranges, integral signs, dx signs. It's like very complicated. I think perhaps for me, the only other place where you get this much written down is when you're doing a big binomial expansion. Then you get a lot of terms like this. But you pull out your calculator and you wind up with 3.08. I think that's kind of cool. Anyway, thanks for watching. I forget how I start that. Does it go?
Here, I
That's
can hope
all
the
for
video was
today.
helpful. I can
What?
hope it.
Now that you've watched the video, write down any questions you still have so you can remember to ask them in class next time we meet. Also note that you can watch the video again if you want to deepen your understanding or patch up any gaps. Finally, give me a like and subscribe if you enjoyed it.